Welcome to another webinar of the Learn by Example series. My name is Lisandro Maders, I'm the General Manager of ENGYS Brazil, and today I will be talking about multi-region meshing within HELYX. Today's webinar goals are to introduce ENGYS and some of HELYX's unique technology innovations regarding meshing, multiphysics, and our graphical user interface, and to obtain a sense of how multi-region meshing can be set up within HELYX. Lastly, we will answer all questions via email post-webinar. You can write all the questions you have by just hitting reply to the webinar invitation email. For those who don't know ENGYS yet, just a quick presentation. ENGYS is a global provider of CFD products and services founded in 2009 in London. We have developers with phone and OpenPhone experience since 1999, and it is because of such highly experienced CFD developers that we were able to provide incredible CFD innovations to our more than 200 customers in the past 10 years. ENGYS has offices in 8 countries, and we have a well-established distributor network around the world. About our products, the key objective of ENGYS Foundation was to join the technological benefits from both open source CFD and commercial CFD codes. The benefits I'm talking about of open source codes are mainly full capacity of customization, being able to dive deep in the source code, and free scalability. And that means that no HPC licenses are required. The user can run as many simultaneous simulations in as many processors as the user wants. But of course, the industry also needs efficiency and high productivity, and for that, an easy-to-use graphical user interface, best-in-class technical support, and an extensive written documentation are needed. And this was exactly what ENGYS achieved as a product, which are HELYX, our general-purpose CFD software for enterprise, Elements, an advanced software suite for automotive industry, and the HELYX add-ons, which are a set of additional modules covering specific applications like adjoint optimization through HELYX adjoint, our block coupled solver through HELYX coupled, advanced libraries for chip design with HELYX Marine, and advanced VOF solver for multi-phase flows with HELYX Hydro. So, regarding today's subject, what is multi-region meshing used for? For several applications, and mostly those who have combined physics to be resolved, like natural and forced convection, heat conduction in solid regions, radiative heat transfer, which has sometimes significant impact on the final temperature for lots of applications, generation and consumption of energy, contact resistance at domain interfaces, extremely important for electronics cooling, conjugate heat transfer problems. And when we have those physics combined, we enable several applications to be properly modeled, like electronics cooling, as I have said, electric motors, and battery cooling is a very emergent subject in the automotive industry. It's a very good example. Heat exchangers, heterogeneous catalytic process, and several others. So before going to the live demonstration, let me talk quickly about a few important meshing considerations when generating multi-region meshes in HELYX. In HELYX, we make use of a so-called zoning mechanism. And a zoning mechanism is basically a mechanism for grouping of cells or faces, generating cell zones and face zones. Most common usage of cell zones are modeling of porous media to model radiators and condensers, for instance, and modeling of reference frames as well to solve moving parts through introducing rotational source terms in the momentum equation for modeling fans through an MRF, multiple reference frame approach. This is another example. And there are also other very common applications like splitting such cell zones into different mesh regions, solids and fluid regions for conjugate heat transfer analysis, for real rotating mesh problems, creating AMI interfaces, and others. And regarding phase zones, those are usually created for monitoring purposes, like surface reports in the middle of our domain, for example. When talking about HELYX, we have two options for the zoning mechanism. The zoning approach, which I called like this because the user can set up this approach in the zone tab in the graphical user interface, and the multiple material points approach. And this will be clearer when I do the live demonstration. Both have graphical user interface support, which is good. The zoning approach requires one unique surface at the interface between cell zones, and that means that no overlapping surfaces are allowed, while the multiple material points approach handles overlapping surface at the interface. So for very complex geometries in which the CAD cleaning for achieving such unique surfaces at the interface, which would be painful, of course, the multiple material point would require less effort compared to the zoning approach. On the other hand, the zoning approach has several advanced options for handling face zones and cell zones, like, for example, better layer coverage control. You can specify layers only in the master or slave patch if you want, and other advanced options. So those are a few comments regarding meshing I would like to have said, and I hope some of them will be clearer with this live demonstration that I'm going to give now. In this live demonstration, I will first set up a very simple case with two boxes and one sphere to demonstrate the difference between the zoning approach and the multiple material points approach. And then I will go to mesh a shell tube heat exchanger geometry with the zoning mesh approach to demonstrate how easy it is to set up it and to show the automated creation of the interfaces between the multiple regions. So let's go to the live demonstration. So for this first case, let's use the multiple material points approach. Let's create a very simple geometry, which will be basically two boxes like this, and a sphere in the middle of box number 1. So let me rename this to box number 1, box number 2. We need to select the mesh algorithm. Let me select the standard one. Base mesh size basically is the maximum volume cell size that we want in our domain, and all the surface refinement or volume refinement are going to be relative to this size. Let's pick up 0.2 meters. This base mesh size is quite coarse for this surface of the sphere, so we could either apply a surface refinement to refine it a little bit, or let me create a second sphere with same dimensions and at the same location, and this will be a volume refinement sphere. So I'm going to the volumetric section, apply an inside volumetric refinement of level 2. Cool. Now we go to the material point section, and this is where things are different between the two approaches. So for the multiple material points approach, we need to go to the mesh options, which will open a series of advanced options for meshing. And under general tab, we need to check this box on, which is the use multiple material points. Once we click OK, we see this new option here. We can enable the unzoned mesh region, and now we can create our 3 cell zones point locations, which will be box 1, box 2, and sphere. Now we need to place those points in our domain. So the blue one, which is the box 1, is already inside box 1. The green one, we need to move to the box 2. Okay. And the sphere, we know that the location is 1, 1, 1. So we are ready to go. We can create our mesh. And here in the view tab, we can see that we have one single region mesh with 3 different cell zones: the box 1, box 2, and the sphere, right? And also it also creates some faces on. So for example, the box 1 to box 2 faces on and the box 1 to sphere face on. However, what we want really, let's define what we want. We want to have two mesh regions, one here and another one here. And we don't want that the mesh inside the sphere to be a separate region. We want the sphere, the volume cells that are inside the sphere, to be simply a cell zone, which is part of the box 1 mesh region. So we do all of this going to the mesh tab in the region section and clicking on the split mesh button. And here we can see that as default it would split all the 3 different cell zones in different mesh regions, but this is not what we want. What we want is to have box 1 region and box 2 region, and the sphere to be simply a cell zone inside the box 1 region. So let's drag the sphere inside to the box 1 region, and here we go. We can click run. And here is where the magic happens. You will see that the end result is exactly what we are looking for. Now we have 2 regions, box 1 and box 2, right? So if I turn on the volume mesh for box 1 region and also for the box 2 region, you see, and inside the box 1 region we have 2 different cell zones, the box 1 itself and the sphere cell zone. And also it creates automatically the interface between the 2 regions. So this one here is the in green is the interface between the box 1 and box 2 region belonging to box 1 region, and the corresponding patch pair is box 2 to box 1, which you can see as blue here is the same as the green one. Alright, so we achieved what we wanted using the multiple material points approach. Now let's go to the same problem. So let me create a new one, which I will call simple case zoning approach. And I'm going to create this exact same geometry. So this is box 2. This is box 1, a sphere, and another sphere to apply the volume refinement. We want an inside refinement level of 2. Let's change the base mesh algorithm default. And now for the zoning approach, we don't need multiple material points. Actually, we only need one material point, and its location is quite important because the mesh algorithm will start meshing from the material point location. So let's think about this. Once the mesh algorithm starts from this material point location and it finds the surface of box 1, right now as it is, it will simply stop meshing. So we would only have mesh here, we wouldn't have mesh here. And the same thing applies to the sphere. Once we start from the material point location and the mesh algorithm finds this sphere surface, it would simply stop meshing, understanding that this should be a patch wall, right? So what we need to do is let's tell to the mesh algorithm that this sphere surface here is an internal surface, and we do this in this zone step. So when you select internal surface, now the mesh algorithm will still generate mesh volume cells inside the surface here. But we want more than that. We want to create a separate cell zone for those cells. So in order to do that, we simply check on this box here and we will give it a name of sphere. And we need to do the same thing for this interface, right? Because we want mesh to be generated inside the second box. And here it comes what I have mentioned in the presentation regarding to have one unique interface between cell zones. So if I select only the box 1, I need to split this this surface because this will be our interface. And remember, we need to have one unique interface between cell zones. So I'm going to select now the box 2. And I also split this surface, but this one here we need to delete. Now we achieved what we need, which is basically one unique interface between cell zone 1 and cell zone box 2. Now we need to do the same thing that we did to the sphere surface to this interface. So we are going to select internal, pick this box cell zones, and let's put the name box 2. Now we are ready to go and create our mesh. And you will notice that the result is a little bit different because we won't have a cell zone for box 1. This will be simply part of the region, of the default region. So as you see here, we have those two cell zones, box 2 and sphere, created by this zoning approach. And again, this is all in the same region. So if we want to split the cell zones into different regions, we need to go here again to this split mesh button. As I said, we don't have the box 1 as we previously had as a cell zone because this is part of the default region. But we want this sphere cell zone to be simply a cell zone as part of the default region and not a separate region as it is right now. So let's drag this again to the default region and click run. And here the result is exactly the same apart from the names, but as we had with the multiple material points approach. So we have this default region, and also we have this box 2 region as we did previously. And inside the default region we have this sphere cell zone. Also we have the external boundaries as we had before, and we have this region to region interface in green here. So basically we achieved the same thing. The interfaces were automatically created. Let's go to the more complicated problem. So let me create a new case. Shot tube heat exchanger. Let me select 6 so it runs fast because we are running out of time. And let me import the geometry. And I was planning to do, as I said in the presentation, this through a zoning approach. However, since it would require that I split this geometry here in order to have one unique interface, I am going to change and do through the material points location approach since we are running out of time. Okay, so we are going to select the standard algorithm, base mesh size, let's put 25 millimeters. And for those baffles which are responsible for mixing the fluid and enhancing the heat transfer between them, let's select a refinement level of 2. For the outer shell and for the plates, a refinement level of 3. For the tubes as well, let's select refinement level of 2. And for the other geometries, a refinement level of 1. I'm not going to apply layers here since it would take a little bit more than I think we have in terms of time. But now in terms of defining the regions, again, we could do this through a zoning approach, selecting here internal as we did with our last simple case, but let's do this through the multiple material points location. So we go to the mesh options, enable this option, use multiple material points. This will open those options here. Let's create a cold region. And the point location for this one, I think it's exactly in the origin, so we are fine. And hot region. And let me see where we are here. So we need a little bit down. like this. Yes, we are fine with this, and we can create our mesh. So it will take a little bit time. Let's wait. Now we have our mesh done, and again we have one single mesh with those two different cell zones, the cold region cell zone and the hot region cell zone. But we want these as separated regions and not simply separate cell zones. And in order to do that, again we go to the regions section and click on the split mesh button, and we want this like this. We want to separate those two cell zones in different regions. So let's click run. And even though this is a quite simple case as well, it's already clear that this automated creation of the interfaces between regions by the graphical user interface saves a huge amount of time. So here, for example, we have the interface cold region to hot region, and this is exactly the same interface for the other region. So they are a patch pair, and doing this manually would be extremely painful. I would say almost impossible for certain cases. Recently, we have a huge CHD case for a customer here in Brazil, in which the case had around 350 regions, and this resulted in 1,500 interfaces. So you can imagine how this would be if we didn't have a graphical user interface with such highly automated interface creation. It would be practically impossible. So this is the resultant mesh. The interfaces were automatically created. If we go to the setup tab, we see that those are automatically recognized as interfaces. So we have these mapped wall type boundary conditions, which does this coupling for the energy equation as it should be. And I think that's it. We are running out of time, but I hope it was clear the two different zoning approaches, multi-region meshing approaches through the simple cases. And I meshed this slightly more complicated case to demonstrate it in a more real scenario. I hope this was clear and insightful, and let's go back to our presentation. So a few take-home messages before finishing. HELYX graphical user interface offers a robust multi-region meshing approach with an automated zoning process with automatic creation of the interfaces between regions. HELYX is vastly used in the industry for cases which require multiple region meshes like CHD cases, and HELYX has replaced other CFD commercial software in the market for several companies. I don't know if you have noticed, but there was no need to extract the volume mesh from the CAD geometry and to make a surface mesh prior to the volume mesh, which is a step commonly required for most of the CFD commercial software in the market. And this quite costly step is not necessary in the HELYX meshing algorithm. Lastly, don't forget to follow our social media. Check our blog at blog.engys.com for our full schedule of webinars. And on this Thursday, we will have an Elements webinar in which Gustavo Almeida will be talking about the coupling between elements and Titan for aerothermal simulations. Again, for questions, you can reply to the email invitation for this webinar. And thank you very much for your attention.